Hi. In this short tutorial, we will demonstrate how to incorporate spin-orbit coupling effect in density functional theory calculations using Quantum ESPRESSO. We will also go through how to build supercell and slab structures. Performing a density functional theory simulation involves following steps in our web platform. First, we need to specify the material system by creating or uploading a material structure. Second, we have to specify the workflow steps. These two steps can be carried out in any order. You may either create the structure first and then workflow, or the other way around. Note that you may skip the above steps if you already have the required structure or workflow in your library. You may also find the structure and workflow you are looking for in our extensive materials and workflows banks, respectively. Finally, we need to create and submit job, where we can specify the materials system, the workflow steps, and compute parameters as suitable for a specific calculation. For current demonstration, we will generate the material structure using Materials Designer in our web platform. Navigate to Materials tab. Click Create. Let's clone the existing structure and modify it. We will create bismuth selenide slab. Bismuth selenide is a prototypical topological insulating material, which features a bulk bandgap and conducting surface state. Bismuth selenide has hexagonal crystal structure. Set the lattice parameters and atomic positions accordingly. Here we will create a slab which has a surface in order to show the topological surface states. Keep in mind that density functional theory calculation can only be performed on periodic systems. We can create surface by adding finite vacuum to the unit cell. We add an extra selenium atom to the structure, which actually belongs to the next unit cell in the periodic system, and equivalent to the selenium atom at coordinate 0, 0, 0, so that we are not left with dangling bismuth bonds. To add vacuum layer, we select preserving the interatomic distances and increase the lattice vector c. Here we added a vacuum of about 10 angstrom in the AB plane. If we enable the repetitions, it will be more clear that every layer is accompanied by a vacuum layer. Now let's save the structure. Note that instead of monolayer slab in this case, we could build slab with bilayer or any other supercell. You may like to explore various advanced options to build structures in our platform. Next, navigate to the Workflows page to specify the workflow steps for spin-orbit coupling calculation. We are going to use latest version of Quantum ESPRESSO built with Intel libraries. For spin-orbit coupling calculation, we will need fully relativistic pseudopotential. Click Edit Unit and select PWSCF-SOC template. Add next unit for the bands calculation. Select PW bands SOC template. Finally, add the bands.x post-processing unit. Save and exit workflow. Finally, navigate to the Job Designer. Create a new job. You may create it under a specific project or inside the default project. Select bismuth selenide slab as material. Select bismuth selenide spin-orbit coupling workflow. Now click View Unit. We will see template with various Jinja variable placeholders. We can also preview the actual rendered input file. The variables in Jinja placeholders can be modified in the Important Settings tab. If necessary, one can override an input parameter or add new parameters by directly editing the template. For example, we can add better convergence threshold for self-consistent field calculation. Similarly, you may want to edit other input templates. Let's navigate to Important Setting tab and update various parameters as suitable. Specific to spin-orbit coupling calculation, we can set the starting magnetization for each atomic species. In this case, both are non-magnetic atoms. We could also start a calculation from a previously converged calculation that was done without spin-orbit coupling enabled. Explore other available advanced options. Scroll down to bands calculation. Here we can edit the k-path for bands calculation and number of points between specified k-points. We would like to increase the density of k-grid for self-consistent field calculation. Navigate to the Compute tab. Here we can adjust time limit, cluster, queue, number of nodes, and number of processor cores. Save and exit Job Designer. Finally, click the Run button to submit job. Once the job is finished, navigate to the Results tab. Here we will find summary of various results including the band structure plot. If we zoom in, we can see the bands near the Fermi energy more clearly. Note the band structure we are currently looking at was obtained with coarse convergence criterion. You need to increase the k-grid density and stringent energy threshold to see the topological Dirac states clearly. You can compare the band structure for slab and bulk calculation and identify the surface states. All output files can be found under the Files tab for further analysis. Thank you for watching this tutorial. Now explore more yourself at platform.mat3ra.com.